Thanks, Mr. Chairman. Well, this research is actually a part of a bigger project dealing with additive manufacture likely structures. So this explains this large number of co-authors that have skills in different areas of engineering, so manufacturing, metallurgy, and structural integrity. Well, some of us last year carried out a research of an easy 316 steel in the rolled state, so not additive manufacture state. And this work was about the low cycle fatigue properties and cyclicity properties of this type of rolled steel. So within this project, we were interested in investigating the behavior of this steel in the additive manufacture state. So we started a literature survey, and surprisingly, we found out that there are not, at least based on our survey, we found out not so many works dealing with the additive manufacture AEC 316 steel. And even more surprisingly is that, if you look here, these works are carried out under different experimental setups, or for example, different specimen geometries. So of course, comparing this data could be somehow difficult. And even more surprisingly is that if we look, for example, at this data carried out with similar or comparable experimental setups, the results seem to be not so comparable. So for this reason, we decided to carry out our own experimental research dealing with the low cycle fatigue properties and cyclic plasticity properties of a laser powered by fusion AEC 316 steel. And then the goal was to compare our own results with literature data, not only for the additive manufactured steel, but also for our rolled not additive manufactured steel. So basically, this is the outline of my presentation. I will briefly describe the material specimen fabrication. Then I will describe the experimental setup and show you some results, and then I will compare them to the literature data. So now, let's start with the specimen fabrication. Okay, we started with a powder of this material, then we used a laser powered by fusion process in order to manufacture vertical rods with length 180 millimeters, diameter 23 millimeters, and we used a sort of chest for scanning pattern. You can see here on the top there are different islands, and in each subsequent layer these islands are rotated 90 degrees in order to assure a more even structure. After that, we took these rods and then we performed a stress relief, heat treatment, and then a machining process in order to obtain such kind of dog-bone specimens according to the standard. Before carrying out the tests, we also performed some microstructural analysis, and as you can see here, this is a typical microstructure of an additive manufacturing material, so you can see very easily the melt pool boundaries here. There are some small regular pores here, and also you can see here the difference in the microstructure for adjacent layers which are rotated 90 degrees. We also perform analysis at higher magnification in order to reveal the grain structure, which is formed by a cellular dendritic submicrostructure with growth in two orthogonal directions. Then we perform the tests. These are low cycle fatigue tests in push-pull condition, strain control, and in each test we monitor the maximum and minimum stress and also the entire stress strain cycle at prescribed intervals. So now I want to show you some results, starting with the cyclic plasticity behavior. First of all, this is an example of stress strain cycle, and as you can see here, there is a decrease in the tip stress. So this material exhibits a softening behavior, as also observed in the first presentation. And this softening behavior occurs for any of the tests. Then we consider this plot and we replot this trend by using a linear scale, and also we normalize the number of cycles to the number of cycles to failure in order to detect the change of the softening rate. Here you can see that there is a sort of plateau. Okay, it is not exactly horizontal, but we can consider that the behavior at mid-life is representative of a sort of stabilized state. So we consider this, this behavior for the next modeling, for the modeling and fitting of the models. Now also we investigated if whether this material has a massing behavior, and it has. In fact, we translated all the stress strain cycles to the origin, and as you can see, okay, it is not perfect, but it is almost a massing behavior, and therefore, first of all, we also try to fit the cyclic stabilized stress strain curve according to the Rambert-Osgood equation. Here you can see the fitted parameters, and then also we compare the monotonic stress strain curve, here the experimental stress strain cyclic points, and also with the fitted Rambert-Osgood curve. Another point is that since the material has a massing behavior, this allows us to use the parameters here in order to compute the plastic strain energy density directly from these parameters. And we computed this quantity in order to perform a fatigue life estimation. And I will show you the results shortly. So now concerning the low cycle fatigue strength, first of all, as I told you, we tried a correlation between this energy parameter and the number of reversals to failure here. This is the fitted line in log-log scale. Well, the fitting would be considered pretty good, although there are some points that deviate from the average line. And in addition to this energy life model, we consider and fitted the more common massing coffin model. Okay, and again, the fitting seems pretty good, apart from one point. So we decided to further investigate this point, tested at 0.7% strain amplitude, because you can see here that this point failed much earlier than the average massing coffin curve, and even earlier than the next point tested at a slightly higher strain amplitude. And we found out, after some fractographic analysis, that the cause of the failure, this premature failure, was a very large lack of fusion defect in this space. So now, as I told you, the aim of this work was not only to perform some tests, but also to compare these tests with literature data. In particular, data concerning additive manufactured steel, but also our own data concerning a road material. I want to start first with the comparison with additive manufactured materials, but as I told you, we cannot consider all the literature data, but we must restrict our attention to only those studies that have experimental setups that are comparable, somehow comparable to our testing setup. So we restricted our comparison to these three works. And here is an example of comparison concerning the cyclic stress strain curve. These the red points here are the experimental results from our work. And you can see that there is a good correlation with literature data, although our points seem to be placed in the top part of this figure. And then we also compare the strain, the fatigue life data of our work with literature data. Again, here you can see that there is a pretty good correlation of our data with literature data, apart from the data from Shrestha and others that show a much earlier, much shorter fatigue life. And this seems to be caused by much larger lack of fusion defects as documented in the article. Now I want to move to the last part of my presentation by showing you the comparison between the additive manufactured 316 steel and the same steel in the road state. As you can see here, I want to start with the cyclic plasticity behavior, showing the evolution of the maximum stress during each test. It's very striking the difference between the two materials. As I told you before, here the additive manufactured material shows a very small strain hardening at the beginning of the test, and then a continuous softening for any strain amplitude. By contrast, the wrought material shows a very intricate, let's say, behavior. There is an initial strain hardening, then a small strain softening depending on the strain amplitude, and then there is a secondary hardening until failure. And this secondary hardening does not appear in the additive manufactured material. For this reason, if we compare the monotonic and cyclic curves, you can see that, of course, as I told you, additive manufactured material shows a very clear softening behavior. On the other hand, the raw material shows a very pronounced hardening behavior. But it is interesting to note that despite this very different cyclic plasticity behavior, at first sight, the fatigue-like behavior seems pretty close or similar, let me say. But we try to fit the regression lines for both models, Manson-Coffin and energy-based model, and also we perform a statistical test on the slopes of these two fitted regression lines. And this is a statistical test based on the Fisher variable, and this test revealed that there is a statistically significant difference in the slopes. So we can conclude that also for what concerns the fatigue-like behavior, these two materials indeed have a different, not so pronounced, but a different fatigue-like behavior. And so I want to conclude my presentation just showing you another a picture concerning the difference in crack nucleation size. As expected for the additive manufactured material, crack nucleation occurs at internal defects like pores or lack of fusion defects, which, as I showed you before. By contrast, for the raw material here, a typical crack initiation site is at the surface, at a surface flow. So now I can conclude my talk by summarizing some main findings. I show you some experimental tests concerning an additive manufacture, easy 316 steel. I showed you some results concerning microstructural analysis and mosaic fatigue tests. The results shows that this type of additive manufactured steel shows a very pronounced cyclic softening until failure, and also shows a massing behavior. And this behavior is also observed in other literature studies. Then I also showed you that differently from the additive manufactured steel, the raw material exhibits a quite different behavior. In particular, shows a secondary hardening not observed in the additive manufactured material. Finally, for what concerns fatigue strength curves, we tested two different approaches, Manson-Coffin and energy-based, and we found out that from a statistical test they have a statistically significant difference in the slopes. And finally, also, there is a difference in the crack initiation sites that are gas pores or, let's say, internal defects for the additive manufacturing material, while the crack nucleation sites are at the surface of the raw material. So I would like to thank you for your attention.
It is time for a quick question, yes? Yes, yes.
Please, what about the role of residual stresses in your material?
Sorry?
What about the role of residual stresses in your material?
Well, we perform a stress relief treatment before manufacturing the specimens, so I guess that there is no such an effect.
It means long-range stresses, but these short-range stresses, do you investigate it?
No.
Yeah.
Thank you, Dennis, for your presentation. Can you maybe comment on the initial significant differences in yield stress between two differently produced specimens?
Between the two
so
materials.
the raw ones and the
Well, of course, this difference is related to the microstructure. Unfortunately, I'm not a metallurgist, but I try to answer anyway your question. I think it's related to the different microstructure of the two materials. And if I remember right, for the road material, this behavior is related to the biphasic structure.
So basically, you're comparing two rather
Also
different
for
materials.
the,
It's not
of
just the
course,
manufacturing process,
yeah,
but there is other aspects as well.
yeah, of course, also for the additive manufacture material, the manufacturing process is different. So you have maybe a higher cumming rate because you are adding material at each layer. So maybe this gives a smaller grain size, so this may increase the yield stress compared to the raw material.
It would be interesting to see how they perform when the raw material is also perhaps heat treated to achieve similar microstructure. But this is another story.
Okay.
Thank you very much.
Thank you so much again.